Hey everyone, so in this video we're going to go over the 2008 AP Physics C Mechanics Free Response number 3. In this problem it asks, in an experiment to determine the spring constant of an elastic cord of length 0.6 meters, a student hangs the cord from a rod as represented above, and then attaches a variety of weights to the cord. So for each weight, the student allows the weight to hang in equilibrium, and then measures the entire length of the cord. The data are recorded in the table below. So for part A, it asks us to use the data to plot a graph of weight versus length on the axes below. And then after that, to sketch a best fit straight line through the data. This question is very easy because they already give us the table of weight and length. And then they give us the weight on the y-axis and the length on the x-axis. So all we have to do is transform the points that we see on this table and plot them on the graph. So for example, the first point we have is at a weight of 0 newtons, the length is 0.6 meters. That makes sense because if there's no weight on the string, the cord is just going to lie at its natural length, which is 0.6 meters. So what we have here, we can just look at where it says 0 newtons and then look where it says, find where it says 0.6 meters, which is right there. So you can just plot a point there. We can follow the same process for all the other points in the graph or in the table. So for 10 newtons and 0.97 meters, that'd be right there. And then do the same thing for all the other points on the graph. It also asks us to sketch a best fit straight line. That doesn't really mean to plot a line through every single point, like connect the dots. It's more find a line that follows the general trend of the data. So like something like that should do. We just want something that shows that as weight is increasing, the length is also increasing, the string is stretching more because there's something heavier on it. So that's what this line is supposed to show, just a general trend. So part B asks us to use the best fit line we sketched in part A to determine an experimental value for the spring constant K of the cord. So in this part, we should think about the equation F is equal to Kx. We want to look at this cord as a spring. They basically say it here, the spring constant of an elastic cord. That's implying that this is a spring and it acts in the same motion that a spring would. So we use this equation to develop an analysis that will help us find the experimental value. So if you think about it, what is causing the cord to stretch? That's obviously the weight. The more the weight, the more the string stretches, as we can also see in this graph here. So in this situation, the force that we're focusing on is the weight that's attached to the end of the string. And just keep in mind that the unit is newtons. And x is how much the string stretches. And that is used, that's the unit is meters. So if we solve for k here, we'll get k is equal to f over x, which in this situation is equal to weight over length. Because as I said before, the force that we're focusing on is the weight, the force that's caused by gravity. That's the thing that's causing the cord to stretch. So that's the force. The length is just simply how much the cord stretches. So if we look at this graph here, weight is on the y-axis, length is on the x-axis. If you think about the concept of slope, slope is equal to rise over run, which is just the change in y over the change in x. So since weight is on the y-axis, the change in y can be denoted by weight. The change in x is simply the length. So the slope is k. It's the same exact thing, right? The slope is equal to k. And then we can just find the slope of the best fit line. It's just an approximation. We can just take any 2 points that'll make the calculation easy for us. I took this point right here, 0 newtons and 0.6 meters, and then this one. So just you can take anything. You can take this point or this point. It really doesn't matter. But I just, for my purposes, I took this point. Which is about 1.4 meters and 20 newtons. And if you do the calculation, change in y over change in x, you get 25 newtons per meter. So for part C, we have a new situation here. The student now attaches an object of unknown mass m to the cord and holds the object adjacent to the point at which the top of the cord is tied to the rod, as represented above. When the object is released from rest, it falls 1.5 meters before stopping and turning around. And then we can assume air resistance is negligible. So for part C, we're asked to calculate the value of the unknown mass m of the object. So what I have here is the two situations that we're worried about in this part. So the first situation is when the mass is held at the top, right? Holds the object adjacent to the point at which the top. So just right there. And then here we have it when it's at the very bottom and just before it's about to turn around. So for part C, these are the two scenarios we're worried about, and I'll get to that in a second. In order to calculate the value of the unknown mass of the object, we want to think about the initial energy and the final energy. In this situation, energy is conserved. We can think of this as an isolated system. So the initial energy is equal to the final energy. So all we're worried about is the initial state and the final state. In the initial state, the only force that's acting on m is the gravitational potential energy. It's just gravity. The string is not stretching here, right? Because it's very loose up here. So it's not stretching. When we get to this point, the only the only potential that we're worried about is the spring potential energy. And we're taking this point right before it's about to turn around, the zero potential energy point. So at this point, we're going to assume that the potential energy is zero. And the reason we can do that is because we're worried about the change in gravitational potential energy. We could, if you wanted to take, we could take, this orange line right here, we could take that as a zero potential energy. And if you think about it, we'll still get the same exact change in gravitational potential energy. Because in the end, the change is just, if you look at this formula here, it's mgh. We're really just worried about the change in h, because m and g are constants. So even if you took this point here, you still get the same value for change in h. So just to make our life easier, we could just take this point as zero potential energy, because it really doesn't make a difference. So the initial energy, so that's the energy in the initial state. That's gravitational potential energy. The formula for that is mgh. In the final state, we just have spring potential energy, so that's half kx squared. That's also just the formula for the spring potential energy. And then we can solve for m, because that's what we want. So m is equal to kx squared over 2gh. We just divide the g and the h, bring it to the other side. So in the previous part, if you remember, we found that k is equal to 25 newtons. We're going to just look at that really quickly, right? 25 newtons per meters. And then we have, for x, it's 0.9 meters. So that might be confusing at first because here it says that it falls 1.5 meters. But if you remember, in the question, at the beginning, it said that the length of the cord is 0.6 meters. That's the unstretched length. That's the natural length. So in order to find x, which is how much, x by definition is how much the spring stretches, not the total length of the spring. So x is actually 1.5, right? That's the total length of the string, minus 0.6 meters, which is just the length when it's not stretching. So the total length that the spring stretched is 0.9 meters, which is why we have 0.9 here in x. And then we're dividing by 2, and then g is just 9.8. And then h is that change in height. It's how much this object is falling, as I said earlier. It's 1.5 meters. And if we calculate that out, we'll get 0.69 kilograms.